Okay, this next part, we talked about two systems, types of blood vessels, what determines flow in terms of elasticity, compliance, directionality, and pressure differences and resistance. The last two that we didn't mention in the last video were viscosity, which is how thick the blood is. It will move slower if it's thicker. It also can cause damage to vessels at different points in the vessels. As well as speed of flow or velocity, which is dependent on the cross-sectional area. And there's a slide there that shows you that the larger the area, the slower the velocity. And so oftentimes students will make a mistake and think that a capillary, being very, very small, would have a quicker velocity. Flow would be faster through a capillary than through the aorta, but that's not true because the capillary bed is added together. So every little capillary contributes to the surface area. And so flow through the capillary beds is much slower than through the aorta. The next part of this lecture of cardiovascular function is really looking at the determinants of blood pressure. And there are many determinants, both short and long-term regulation of blood pressure. So we talked about the short-term regulation of blood pressure by looking at the inflammatory process, and these were local regulations of blood pressure, so not necessarily affecting the blood pressure reading. But in the area where there was a tissue injury and there was vasodilation, we know that the flow would change in an area where there was vasodilation because, so I'm going to pause here and see if you can remember the answer, because flow is indirectly related to resistance, which is determined by radius. So if the radius of the vessel is larger, then the flow slows down, which is part of what we wanted during the inflammatory process because we didn't want infection or some kind of foreign body to get into the regular system. So all of those things listed on the slide, nitric oxide, histamine, serotonin, bradykinin, prostaglandins, all those things released during the inflammatory process will affect the blood pressure locally at the site of injury. There are other things that affect the systemic blood pressure in the short term and the long term. So in the short term, that is autonomic control. So it helps to understand what determines blood pressure to begin with. It's determined by the volume of fluid, or in this case blood, within the vessel, as well as the resistance of the vessel, which we know is determined by the radius. So the higher the volume, the higher the resistance, then the more the blood pressure increases. So one of the biggest portions of our short-term control of blood pressure is determined by the sympathetic nervous system, and that is through the release of the neurotransmitters epinephrine and norepinephrine as they interact on receptors in our body called the alpha and beta receptors. The alpha receptors are located on blood vessels. And if an alpha receptor is stimulated by epinephrine or norepinephrine, then the smooth muscle contracts on that vessel, which decreases the radius of the vessel. And if we decrease the radius, then we increase the resistance, which means we would increase the blood pressure. Beta receptors are located on the heart. And if epinephrine is released and interacts with the beta receptor, then we would increase the heart rate and increase the strength of a contraction. And both of those things would increase the volume of blood circulating, which would increase blood pressure. So the sympathetic nervous system will increase blood pressure by activating receptors on blood vessels and receptors on the heart to increase both the volume of blood and the vascular resistance. So what triggers the release of the sympathetic nervous system is the next part. So we can trigger the release or the output of the sympathetic nervous system by stimulating or interacting with baroreceptors and chemoreceptors in the body. So baroreceptors, and there's a nicer picture of the baroreceptors in your PowerPoint slides, but baroreceptors are located in the aortic arch as the vessel leaves the heart, as well as in the carotid, and they're sensing stretch. If there's a decrease in the amount of stretch of the aorta or the carotids, that means there's less volume in those vessels and therefore a decrease in blood pressure. And that would be a signal to the medulla, which is where epinephrine and norepinephrine that release is triggered, to increase the output of epinephrine and norepinephrine to stimulate blood vessels and to stimulate the heart. So this is a short-term management of blood pressure and could be illustrated by how you respond and how you increase your blood pressure just by changing position. So if I'm laying flat and my blood is, in a certain pooled way across my body, and if I stand up quick, then the blood will pool in my legs and there'll be decreased stretch to the aorta and the carotid arteries, which means there will be a signal to the medulla to increase epinephrine, norepinephrine outputs, and then the blood pressure will go up. So I won't feel faint. And that should happen very quickly. So I would never know that there was ever an issue that I ever was going to be faint unless I had a problem managing that, in which case I would have orthostatic hypotension. The other way that the medulla will increase output of the sympathetic nervous system, such as epinephrine and norepinephrine, is by chemoreceptors located in the medulla that are sensitive to an increase in carbon dioxide and pH. And a decrease in pH. So when that happens, when there's an increase in carbon dioxide and a decrease in pH, and it's just a small amount, it doesn't have to be large, there would be an increase in epinephrine and norepinephrine release. And this again makes sense when we think about when people exercise as a way to think about this. So a person exercises, which means we increase oxygen demand on the skeletal muscles, which especially in the short term, or as the person has been exercising for a while, could then increase the production of lactic acid. So it would change the pH, which would increase sympathetic nervous system output in order to increase circulating oxygenated blood to skeletal muscle in order to decrease or get rid of that pH change. The other system, the renin-angiotensin-aldosterone system, is our long-term management of blood pressure control as opposed to the autonomic nervous system, which is the short-term. So the renin-angiotensin-aldosterone system is activated when specialized cells within the nephron sense a decrease in blood pressure or blood volume. And when that occurs, those specialized cells in the juxtaglomerular apparatus will release renin, which is an enzyme that converts angiotensinogen to angiotensin-1. So angiotensinogen is a protein that's created in the liver that is in the bloodstream in its inactive form, just there in case it's needed. If the kidneys sense a decrease in blood pressure and renin is released, that renin is an enzyme that will convert angiotensinogen into angiotensin-1. Angiotensin-1 will then circulate through the bloodstream, and as it comes in contact with angiotensin-converting enzyme that's located in the epithelial cells of the lungs, it will convert into what's called angiotensin-2. Angiotensin-2 is really one of the big endpoints of this system. Angiotensin-2 is a very powerful vasoconstrictor, so it will cause contraction of smooth muscles on the blood vessels, which will decrease the radius of the vessel and increase resistance, thereby increasing blood pressure. Angiotensin-2 will also activate receptors on the adrenal gland to increase production of a hormone called aldosterone, which operates in the nephron to save water sodium. So you increase your blood volume. So the whole point of this cascade of events is increased vasoconstriction. So that's increase in peripheral vascular resistance, as well as increase in blood or fluid volume by saving water, which are both determinants of blood pressure. And so our blood pressure should increase. In which case, the hope is that the kidney would sense that that has occurred, and then this would then shut down because the blood pressure was back to normal. The reason that this becomes a problem in our bodies is because our body is a beautiful evolutionary machine, but the things that we have, the hormone systems and cascades that we have, are really meant for prehistoric person. So during prehistoric times, you would expect to be starved or dehydrated or a victim of trauma from a dangerous animal. And so when you have low blood pressure, it's because you have very low volume. And that is what the kidney is sensing. And then by releasing renin and starting this cascade, I will save fluid and vasoconstrict, and I'll bring my blood pressure up. And for a prehistoric person, that was the perfect way to manage this problem. However, now when we have issues with our blood pressure or a decrease in flow to the kidney, it isn't really related to starvation, dehydration, or trauma. It's related to stress or our other lifestyle habits. So, and this is why the definition of flow becomes important again. So remember before we said that flow equals a pressure gradient divided by resistance. And resistance is determined by radius. And if the radius is smaller, then the flow is decreased. And that was why hypertension contributed to end organ failure. Well, if the person has decreased flow into the nephron because of hypertension, the kidney doesn't know that. All the kidney is sensing is the decrease in flow. And then renin will be released, which converts angiotensinogen to angiotensin 1, which is converted to angiotensin 2 by ACE, which causes vasoconstriction and fluid retention, which in that case would be the last thing we should do, because that will only make the problem worse. So when someone has hypertension, this system becomes a vicious cycle.